possible vector line equation in linear combination form for the following lines given in slope-intercept form. Okay, so I'm going to start with a vector line equation kind of just in that standard form. So if we're doing 62, we know the slope is 3. So that tells me our slope vector is 1, 3. And the y-intercept is negative 4/3, which tells me I can make a point vector of 0, negative 4/3. So we can say that we have the IV component form vector line equation here, right? So what it's asked me to do now is to write it in linear combination form. So it's going to be like something times I plus something times the vector j, right? So remember that I is just the x component. So for this, it would be 0 plus 1t, or just 1t. And then for the j, that's like our y component. Our y component is negative 4/3 plus 3t. And that's be good enough. And that's just kind of like, you know, what did the answer key say? I don't remember how we cleaned this up, if we cleaned it up at all. That's the gist of it. Nope, didn't clean it up at all. Exactly what I have. Okay. Yeah, no problem. So again, just like one of those things, it sounds complicated, right? The words are very scary. But if you think about it, just like all I'm doing is taking the I component making the coefficient for, or the X component making the coefficient for I, and the Y component making for the coefficient for J. It's not bad. Hannah? 86, you said? Sure. So it says sketch the following vector, and we're looking at 88 here. So I'm going to draw myself a XYZ axis. And since this has positives and negatives here, I think I'm just going to use the I'm going to drop in the XYZ from OneNote, just kind of spread that around to make it fit. So just as a reminder, how do we label these axes? Do you remember? If you don't, and maybe I forgot for just a minute here. So the z is the straight up and down, the y is the left and right, and the x is coming out towards us. Okay. I do not, without my normal room set up. I mean, I do, but it's all in the other room and it's all locked up. Okay. I wish I had a better. I'm sure Miss Garcia has one in here somewhere, but I don't really want to feel good about rooting through all her stuff to look for it. Alright. So let's go ahead and start drawing our tick marks. I'm going to do 4 tick marks on the x-axis. 1, 2, 3, 4. And then 5 tick marks on the negative y-axis over here. 1, 2, 3, 4, 5. I'll put like a point on each of those. And that's going to be like 3 sides of my parallelogram. So this is my 2-dimensional point for -5, right? Then what we're going to do is we're going to, in this case, so it's really kind of dropping. I'm going to draw 6 units in the negative z-axis, so like 1, 2, 3, 4, 5, 6. So I'm going to now project all these points down. Estimate these ones, that looks like about 6 units. So that was a little bit off there. So that's my point for -5, -6. But we're not done, right? Because this is a vector. The last thing I need to do is draw an arrows whose start is the origin and whose head is the point that we've just drawn. So that's my answer. Does that feel okay, Hannah? Elena? 89? Sure. All right. So, first thing I would do is I would notice that the vector W is written in linear combination form as opposed to component form. So I'm going to just translate that into linear combination form. So the coefficient on the I becomes my X component, the J becomes my Y component, and the K becomes my Z component. So then I'm going to do 2 times U minus W. So 2 times 2 is 4, minus 3 is 1. 2 times -4 is -8, minus 6 is -14. And then 2 times 5 is 5, minus 5 is 5. Say that right?
Yeah, I accidentally wrote down E instead of U.
Oh, that would do it.
Off.
Yep.
Yep.
Very easy to do that. Giselle,
You're 115.
115. Sure. So all we're going to do, it asks for 3 points on the line. All I'm going to do is just pick a couple values for t. So the values for t I'm going to use are -1, 0, and 1. And then I'm going to plug those into my equation, and the output is going to be a point on my line. So if I plug in -1, I have 3 plus 1, that's 4. -2 minus 2 is -4. 2 minus 3 is -1. If I plug 0 in, well, that's just the point vector. And if I plug 1 in, I have 3 plus -1, that's 2. -2 plus 2, that's 0. And then 2 plus 3, that's 5. Now, there's infinitely many answers to this. Like, there's nothing magic about the values -1, 0, and 1. They're just like the easiest arithmetic values I can pick, so that's why I chose them. I mean, you could pick 7/3 and square root of 19 and like e to the 17th minus 7 or something as your values for t. I don't know why you want to do that, but you can pick any value for t and it's going to output you a point on the line. But pick easy values for t because it's just an arithmetic problem. That's all you're really doing. And this is just like you would find points on a line for like a Cartesian equation, like y equals mx plus b. You just pick values for x, you plug it in, and it gives you your point, right? It's the same idea, except t isn't, these values for t aren't actually any of the coordinates, right? The t is what we call a parameter, as it's the input of the function, but is not actually part of the output. Does that feel okay, Giselle?
Yeah, I just didn't know the process, but it's
Yeah, super easy, right?
Yeah.
Again, most of this stuff, like the confusing part is, like the notation looks weird, like the vocabulary is a lot, but the actual processes that we're doing are either familiar, like we've done this a bunch of different places and just like adapted it, or it's just really straightforward. It's just a question of like, what do I do to do this? And I think that was the hang up here. It's just like what to do. Well, it's the same thing you do for like a mx plus b equation. You know, you just pick some values, plug them in, and write down your outputs. Okay. Anybody else? Elaine.
Could you do 97?
Sure. If I input that yet? 97. All right. So it says to find a possible vector line equation for the line that contains the indicated point and vector in component form. I mean, like, if you have the point, that just can become our point vector. And we have a vector in the same direction of the line. if they want this in component form, is that what I'm confused a little bit by my own direction there. If they're saying the vector we're given is in component form, or they want our answer in component form. So I'm just going to cheat here real quick and look at the answer. This was an odd one anyway, so you would have been able to, okay, so they wrote it that way. Sure. And I did 95, didn't I? Did you ask for 97?
It's fine.
It's the same thing, right?
Yeah.
Okay. So it's asking for this line equation in component form. So rather than writing these as column vectors, I'm just going to write it the same way, except I'm going to write them like horizontally as component form vectors. But that's it. Yeah. Now, if these were 2 points, it's a little bit trickier, but if you have the direction vector already, it's just like plug it into the form and you're done. Now, why does it say possible? No, you don't have to check anything. The possible is that like any vector in the same direction as this one is suitable. So you could scale and multiply that by something, and it still would work. Now, why you would do that, I don't know, but you could, right? And the point vector could be any point on the line. So if you found another point, you could use that one instead. Why would you do that? I don't know, but you could. It's possible. There's infinitely many possible vector line equations here. Now, with what you're given, I don't know why you'd write anything other than this one, but I want to be clear that that's not the only answer. It's just the only reasonable answer that like a sane student would give. All right. So the last topic then in chapter 8, what do we call this section? It's 8.7, I think. Scroll down. This. Maybe it's 8.8. Intersections, lines versus lines. All right. So we're in three-dimensional space. Now, we're working in three-dimensional space. What are the possible interactions we can have with two lines in three-dimensional space? Three of them you should know automatically. Well, when I say interactions, like you have two lines, right, in three-dimensional space. What can happen to those two lines in three-dimensional space? Okay, one possibility is they intersect. How many times would they intersect? One time. Okay. Could they intersect more than once? Braden says yes. How many times more could they intersect? More than two. Infinitely many, right? What do we call that when the lines intersect infinitely many times? Yeah. It's where the two lines are basically the same line. Good. The third outcome would be, what's that? Okay, specific. Well, there's two types of never.
Oh, parallel.
Yeah, parallel is one type of no intersection. The other type is not parallel, but not intersecting. This is the new one, right? The other three were the same as two-dimensional space. What the heck does that look like, Mr. Kulik? Well, imagine we have two parallel planes. So like one plane is just on top of each other, right? You have two sheets of paper that are like in a stack where they're parallel, but they're not, there's no intersection between those two planes. If I have a line on this sheet of paper that looks like this, and a line on that sheet of paper that looks like that, if they're contained inside that same sheet of paper, they're never going to intersect. But clearly, as I've drawn those two lines, they're not parallel either, because I can't take a third plane and capture both of those lines completely in it, right? Everybody agree with that? So that's the new fourth outcome we can have in 3 dimensions. Is that okay? Visually, you can kind of see what's going on here. So what we're going to be asking you to do in this chapter is I'm going to give you a pair of lines in the vector line equation form and ask you to determine what's going on. Are they intersecting, coinciding, parallel, or not parallel intersecting? And if they happen to be intersecting, what's the point of intersection? So what we're going to do is I'm going to just set up a flow chart to kind of describe the process that we're going to use to check this. This is the same flow chart that we wrote when we did this in 2 dimensions, but it has an extra branch to it because we have an extra possible outcome. So let's say that we have R1 we should do alphabetical order. I'm getting confused. We'll call that one S. Okay, so that's our system. A pair of lines. Actually, I should use the word parallel. First thing we're going to do is check to see if R1 has the same direction as R2. What we do that is we take V1 and see if I can write that as a scalar multiple of V2. So what that means is I solve that system of equations for K and check to see if I get the same K every single time. Right? Just like we did in 2 dimensions. So if they have the same direction, they could be parallel or coinciding. If they're not, they could be intersecting or not parallel, not intersecting. I'm going to abbreviate that as NPNI because there's just too many letters to spell that out every time. Everybody cool with the flow chart we're kind of building here? All right. So to tell the difference between parallel and coinciding, we're going to check, does the vector R01 lie on R2? do that, we're going to plug that vector in to R2. And see if you can solve that system, if I can get the same value of t every time. So if it's yes, then we have coinciding. If it's no, then we have parallel. So here we're going to check, does R1 intersect R2? To do that, we're just going to take R1, set it equal to R2, and we'll solve the resulting system. If the resulting system has a solution, we know that they're intersecting, and we plug that solution back into R1 or R2, depending on which value of S or T you solved, to find that point of intersection. If that system has no solution, then we have that not parallel, not intersecting situation. Okay, so this flow chart is something that I would want to get really familiar with and feel comfortable using without looking at it. Okay. So again, the nice part is that every step on here is a step we've done as a standalone, right? Checking if two lines have the same direction, we've done that before. Does a point lie on a line? We've done that before. Do two lines intersect? We've done that before. So it's going to be, the steps are going to be familiar. Let's grab the examples here. Oh, shoot. And I need to use the examples in the book, because these ones are not trivial to make up yourself. It is not something Mr. Cooley can just kind of fly by the seat of his pants and create. Yes, sure. All right. So step one, what do we check first? The direction, right? So I'm just going to take my first direction vector and see if I can write it as a scalar multiple of the second direction vector. Now, who can do this in their head? Well, it's not.
-4.
Yeah, there you go. Yep. So yes, that works. If k is -4, -1 times -4 is 4. -4 times 3 is -12. -4 times -4 is 16. Do I have to write anything out there? Not really, right? Like that's something you can see by inspection. If you need to write it out, though, please do so, right? You're just solving each equation for k. Each line separately as its own separate k and making sure they're all the same thing. So we know that they are either parallel or coinciding. So that's where we're at. Everybody good? What do we do then? See if the point vector from one line is a point on the other line, right? So you could take 233 and plug it into R2, or you could take 307 and plug it into R1. It does not matter. You'll get the same result either way. So I'm just going to take that first point vector and plug it into the second equation. And we're looking to make sure we get the same S every time. So if I just translate this into 3 equations, I just read the first line, I have 2 equals 3 plus negative 1s. If I read the middle components, 3 equals 0 plus 3s. If I read the z component, 3 equals 7 plus negative 4s. So I'm just going to solve these for s. So here I have s equals 1, s equals 1, and s equals 1. So since these are all the same, what do I conclude? This is coincide. Do you feel okay with that example? In general, the steps here can be kind of lengthy, like there's a lot of things to check. But if you understand what the process is doing and like, okay, yeah, to see if they're the same line, if they're parallel, all I need to do is see if there's a point on both lines. All right, let's do the next one. And the nice part about this is the way we've set this up is it's the exact same process every single time, right? Which is lovely because it's just, all I got to do is learn this procedure and learn the little subroutines inside the procedure, and it's always kind of the same thing for me, which is lovely. I really like that. So just like before, I start with checking the directions. So here maybe it's a little bit harder to see. So let's go ahead and check. So if I divide both sides by -6, I get -2/3 for the x. For the y, I divide both sides by -9, I get -5/9. And already I can see, no, they're not parallel. Or they don't have the same direction, right? Everybody agree? So that tells me we're either intersecting or not parallel, not intersecting. So what I do next then is I set the two equal to each other. And I set up my system. And my recommendation to you is if you're a bad penmanship person, don't use S's and T's because they look a lot like 5s and plus signs. If you're a bad penmanship person, like know yourself, just change it to like A's and B's or something where it's like I can't screw up what that is. I'm a bad penmanship person. Like my S's already look like 5s. I'm already concerned about doing something dumb, but I'm this committed this far, so I'm going to see it through and just be careful. But Now that I've written my system, I'm going to translate this into a form where I can put it into a matrix. So I'm going to add 6s over, and then subtract 2 over. I'm going to add 9s over, and then subtract 4 over. And we're going to subtract 2s over, and then subtract 1 over. And then we're going to solve this system. Now, where's my calculator? What do you notice about this system that I've set up? How many variables does this system have? 2. How many equations does my system have? 3. Is that a problem? No. What? Why is this not? Where are you? Where is this thing? Now, come on here, calculator. Yeah, there. Maximize. Ha! How smart at you. You're trying to hide from me. Okay. So, I have these 3 equations, right? I have 2 variables, so I have an extra equation. What do I do? Well, I'm just going to ignore one of the equations, right? Is everybody okay with that? Does that mean that the equation I'm ignoring does not matter? No. I still need to worry about it, just not to solve the system. Okay? So we'll go to matrix, edit, still doing a 2 by 3, 6, 4, -4, and 9, 5, -8. Exit back out, go back to my matrix menu, grab that RREF command from the Math tab, and then do that to matrix A that we just made. So I get that S is -2 and T is +2. And now I need to check this answer. In the 3rd equation. Because just because this system had a solution doesn't guarantee that there's an intersection. This solution may be valid in 2 of the 3 planes, but not actually hold in the 3rd plane. So that did work. That system has a solution. So we know that we are intersecting. To find the point of intersection now, what do? I plug either S or T back into the corresponding equation, R1 or R2. So I'll use T. I think that's the better choice. Why did I say that? There's no negative sign. It's one less thing for me to goof up. So 4 plus 2 times 4 is 8, 10. Yikes. 4 plus 5 times 2 is 14. 1 plus -3 times 2 is -5. So my point of intersection would be 10, 14, -5. most common mistake students make is forgetting to check that your solution with your third equation. It is still possible for the solution or for the system to solve 2 of the 3 equations, but not work with the third. Which is weird, but that can happen. Everybody still doing okay? So we're running through examples? Hannah? Of course. Yeah, no problem. Alright, let's find the next example here. Oh, that was all my examples. I have just the 2 examples. In the notes, it looks like. Okay. That looks good then. That's it for me for today then. You guys happy? So, huge homework assignment now. The last 4 problems. So I think, what does that leave for this weekend? That's what, the 12th is Sunday, right? Today's the 6th. So I think we assign, what did we do? We talked about it last time, didn't we? So it'd be 89 to 122. That's what I meant to press for next time. Something. All right, I'm going to stop talking. You guys can take the remaining, 25, 30 minutes of class here to grind away on your problem set. You know what I mean? The plan for Wednesday will be to do the chapter review, the review day, take questions, let you guys have a day to kind of work on stuff, get caught up, figure stuff out. And we'll probably plan on the test for Friday. You go. Okay.